to follow the recording of our webinar, which handled the Eurocode Generation 2, what I hosted with my colleague Jan. And this is a recording, so it's a bit shorter version of the webinar we had. And we have a lot of interesting content, so I hope you stay till the end. But Jan, go ahead.
Yeah, thank you, Joni, for this introduction. Yeah, as you mentioned, this is a recording. We'll talk about the second generation of Eurocode in FEM-Design. What are the plans for today's meeting? This is firstly, I will talk about second generation of Eurocodes in general. Then I will present our implementation roadmap. Nextly, we'll focus on selected changes, and those are selected by us, so most interesting in our opinion changes. Then there is no question and answers in this recording, but in the webinar there were question and answers. General information about second generation of Eurocodes. Question you may ask is why we have the new generation at all. Because there are new methods, new studies, new materials, new regulatory and market requirements, new requirements for existing structures, new requirements for robustness. The idea was also to improve the practical use for day-to-day calculations and to reduce the number of national dependent parameters, so more unification between the markets. When you take a look into the structures of the codes, you can see no much difference here. The only difference are three new parts of the structural glass, fiber polymer composite structures, and membrane structures. You may also ask when we will have the new codes, and the answer, simple answer is now. We are already past the first of the key dates, so this is the date of availability. This is the date when all the defined version of the code should be ready and after formal voting. Right now we are in the middle period, publication period, until the end of September 2027. All codes on the national level should be published, and then we have only half of the year, 6 months, to withdrawal of the existing generation of the codes. So you can notice how tight the schedule is. And you may also ask, is it real or what is the status of the implementation? And I have a graphic from the Eurocodes website from the mid-January this year, and you can see here that all seems to go as planned. Almost all the parts were in the middle of the January ready. Only a few of them during the voting or some other proceeding. And I made a short summary how many changes there are in the codes by simply adding the pages part by part, and you can see we have over 47 parts in the new codes, over 8,300 pages, and this is 70% more pages than the first generation, so pretty big improvement in the page count. For sure, you don't need to read every page from the new generation, but I think whatever you are designing, it will affect you anyway. And how about FEM-Design? How we are going to implement the new Eurocodes? Here I can risk a statement that FEM-Design is one of the first softwares on the market where second generation of Eurocodes is implemented to practical usage for engineers. In the upcoming version 25.1, there will be implementation of Eurocode 0 and 1, so basics, the concrete design, and masonry design. This update is planned in autumn 2026. Nextly, we are going to focus on steel structures, then the rest, so the timber, composite, and foundation structures. And you may be sure that we'll publish or implement all the design modules before the September 2027. Probably after this date, we will need update due to some national annexes. So everything is ready before date of withdrawal. In software, it looks like that. You can select the generation in the dialog at the very beginning when you open the program. You can also check the status of the implementation. You can always change the code in the settings as before, and in every view you can quickly check what code you are currently are in left top corner. And we are going towards the changes. Firstly, Eurocode 0, so load combinations. Please be aware that all the changes we are going to present are from the basic versions of the codes, so national annexes may change a bit here in your country. First changes in consequence classes. Previously we have 3 of them, now we have 5. But Eurocode still covers only the middle 3. Although you can use Eurocode to design also due to consequence class 0, staying on the safe side. And those consequence classes are maybe right now more strongly connected with the load combinations and more used due to consequence factor. More on that later. So if you are designing anything from the simple storage house to the high-rise building, you can still use only Eurocodes. But if you are designing something like a nuclear power plant or dam, you maybe need something more. On the next slides, I will present some changes in the load combinations and in the load combination factors, and all of this will be on ultimate limit state example, so please be aware. When we take a look into the basic equation, it's still the same. So the effect of action should be lower than the resistance of the structure. And the only difference in the next equation you can notice is this XRD part, and this is the coefficient or the part due to material resistance. So now this equation is also compatible with geotechnical design. Previously, something like that was in Eurocode 7. Nextly, in the equation, you have a lot of partial coefficients next to every type of the action, and this is still the same in the updated code. So you have gamma f factor, partial factor on action. What may be new is the partial factor on effect of action, gamma e, and this partial factor seems like a new thing, but actually this is not a new thing. In previous code, in the text, you already had information that for some specific type of analysis and structures like ropes, cables, and membranes, you should use gamma f for effect of action. Now it's the same, but stated with the maybe more elegant way, with separated naming, gamma f and gamma e for factors. You can notice in equations that right now we have 3 sets instead of 2, but new equation 812 is the old 610, 813 first part is 810A, 813 second part is 810B, 610B, sorry, and new set is 814, but the second part of 814 is 610B, and in the first part you have only the permanent action. And this is also not a new thing, because a situation like that was in the node below one of the tables. So 8 and A, there is information that it may be used this way, so only permanent action. Maybe the new thing is information below the equations. The default formula is 8, 12, so the single one. Next changes in the coefficients are based on the building annex. Also here you can see that in the new code you have in Annex A more parts for all different kind of buildings. So all partial factors should be in one place. Combination factors table is now much bigger. We have the categories F and G connected for vehicles and also coefficients for vehicles higher than 160. Some small change for category H, new categories for roof with access, new category for stairs. Terraces, balconies, construction actions, icing, water actions, and waves are also included in the same table. In FEM-Design, it looks like that. You can select consequence class and consequence factor here. You can see all updated equations are included. For any of the load group, you can select from updated load category table. And as always, you can quickly generate combinations from load groups according to the updated codes. The new thing may be single source principle. In short words, this is the principle when the point of this principle is if your loads are correlated with each other, you can consider their effects together. It may not look like a new thing and seems natural, but you have also information that for cell weight of the structure ground, it's usually like that. But if permanent action has both favorable and unfavorable part, you can use this principle only when the structure is non-sensitive to this change of the spatial or magnitude change of this action. And you have also information that when your check is with static equilibrium or uplift check, you should split the permanent action into stabilizing and destabilizing parts. I have an example of the simple beam here. Simple beam with the cantilever part, and we are going to talk about the bending moment in the span. So from dead loads only with single source principle, so the same partial factor for the dead load action. You can see some bending moment, but without this principle, you can see, of course, different bending moment, and this difference is pretty big. So because it's 46% when we add live loads. This difference is much smaller, but still may be significant in your design. So, in my opinion, usage of this principle is always at the designer choice. Nextly, in old code, you had some different states in your design: geostate, str state, AQ state. It's not the case anymore. We have verification cases from verification case 1 to verification case 4. And verification case 1 is the structural resistance in both structural and geotechnical design. Verification case 2 has two parts, A and B, and this is loss of static equilibrium and uplift, or strength of this element when element is connected with the equilibrium check. This is also connected with the single source principle, and verification case 3 and 4 are due to geotechnical design. So we can say those three sets, three tables from Annex A in previous code are now in only one table. This table is big and with a lot of nodes below. I will focus on most important, in my opinion, parts of the table. But it's pretty similar than before, so we can say there is a sequence B, A, C of the previous tables. And the most important thing maybe that the base partial factors are still the same. So we have 135 for the permanent actions and 1.5 for the variable actions. And you can also see in the table KF, so this is consequence factor, and this consequence factor is not next to every of the factor, but only next to some of them. So please be aware. And next change is adding the water, a separate type of the action with a bit different coefficients. And you can see that for every verification case, from verification case 1 to verification case 3, for favorable action, permanent action, it's always 1.0. And assuming you are not designing the geotechnical structure, important for you may be verification case 1 to 2. And how to understand it. Verification case 2b is like you have basic the case, but you treat all the permanent actions as favorable. And verification case 2a is maybe more complicated. It's used only when you have permanent action with stabilizing and destabilizing part. Then for the stabilizing part, you have reduced factors. Please notice here that you have no factor lower than 1.0 anywhere in the table. And the new part may be the bottom of the table, so the gamma E factor for the effect of action used only in verification case 4. I have also an example here. So when we are going to check the equilibrium, so the uplift of the left support in the similar beam than before. In previous code, we have AQ state, and from this state, it was we have small uplift in this support. And when we are going to design the anchorage or the beam due to this uplift, you can see there is no uplift in the STR state. So how to design it? Previous code had node due to the situation like that, and you can design anchorage for the combined verification of the resistance and equilibrium check with different partial factors. And this is exactly what's going on in verification case 2 A and B in the new code. There is no uplift in the case of this beam. It might be in for different beam for sure. So you can see this looking as complicated at the very beginning. I think with single source principles and all that is not a big change between the codes. And in FEM-Design, we are not pushing the verification case naming. You can see and always change the factors here. You can also do your load combinations manually in the table if you want. You can also set custom load cases relationships. You can also do custom combination methods if needed. Next change, snow load. So Eurocode 1. And first thing new for you may be the scaling factor due to climate change. It's included in updated FEM-Design here. It's 1.0 for now, but maybe bigger in next years. Next change is for flat roof. You may want to use rain on snow surcharge load, and if you tick this button in FEM-Design, it's done automatically. You can also notice some small difference in naming. So drifted is now unbalanced load for snow. We are following the updated code naming. And when we take a look into snow on roof basic equations, you can notice one big difference here. So no exposure coefficient in this equation, but exposure coefficient is still in the updated code as it was before, and is also included in FEM-Design, so it has to be used somewhere. And it is. I will talk a bit about that later. For flat roofs, in every case you had 0.8 coefficient. It's not the case anymore. It's 0.8 times exposure coefficient for flat roof. So here you have this exposure coefficient hidden. So you may say this shape coefficient is not shape anymore, it's shape plus exposure. And exposure coefficient for flat roof is not exposure coefficient, it's more complicated. This value is varies between the exposure coefficient to 1.25 based on the effective roof length, and this effective roof length is calculated from equation like that. And 1.25 is not random. This 1.25 times 0.8, this is exactly 1.0. So from the falling snow perspective, it's like the falling on the ground. So big roof is like the ground right now. And what is the difference between the code? We have also the chart like that. For roofs, when the effective roof length is lower than 50, you have no difference, and then the biggest difference is for roofs above 400, and it's up to 56% change. Between codes depends what exposure coefficient you was before. And I made also additional analysis. So the simple rule may be if your longer side of the roof is lower than 50 or the shorter side is lower than 25, then it's like old code. So you are in the first part of the chart. And the good news is that FEM-Design calculates this automatically for you, whatever roof size you have or whatever shape you have, the proportions of the roof dimensions. After you add the climate panel for flat roof, you can quickly generate the snow load, and depending what size it was, FEM-Design calculated it automatically. You can see here this from 0.8 to 1.0. So the load on the ground for the bigger roofs. Next change for pitched roofs. We have still three cases. Case 1 is similar, but case 2 and 3 are different. You have snow load on the one side of the roof, so no half of the snow on the other side. And this is the change in arrangement, but there is also a change in the value. After you add the old line to the new chart, you can see the difference in the maximum slope of the roof. This is 70° instead of 60, and this orange is the exposure coefficient influence. You can see the biggest change is for 30° roofs, and it's up to 50%. So also maybe significant. And please remember, you have the arrangement change and the value change. So I have a simple example here: dual pitch roof with the same snow load value in case 1, but in case 2 and 3 you have 20% difference. So from 0.8 to 0.96, but also the change in the arrangement. And the result changes even bigger. It's 93% when you compare the maximum displacement of the roof structure, so pretty big change, and it's 61% in bending moments in my case, of course. But I think when you have situation like that, 30-degree or close to that slope, there will be always a change in your roof load. And next roof, multi-span, you have change in both balance and unbalanced load. For balance, you have a constant coefficient in the middle part, and for the unbalanced, you have different arrangements, so only the snow in the middle of the roof, and also more conditions. Also due to the height of the roof. So we might say that right now it's not the load is not following the line; it's following the area below the line, and also the basic coefficient is higher. So we are starting from 0.9 instead of 0.8. Next, maybe not the change, but the new thing in the code is flat roof with title panels. It's added. You can calculate it now. And then also the new thing, roof close to the taller construction. It was always in the code, but right now we have detailed calculation method for the constructions when there is a gap between them. Also, a good thing here is that all those changes I mentioned about are right now included in FEM-Design. You can see a bigger configuration dialog here, and I have short example. I am adding the climate load panel with title for flat roof with title panels. You have to select the slope of those panels. Then you can change the height of those, and after that you may want to configure additional edge objects. I did it before, so I just generate the load, and you can see all the load cases are there due to all kind of different checks. Also this title panels, also multi-span roofs, everything there. Added to one load group with custom load group relationships, ready to use in your design. Next, Eurocode 2, so concrete design. Concrete and the table 3.1. I'm sure you know this table, and this table is named 5.1 now, and it's much smaller as you can see, but I made it bigger so we can directly compare and see the changes. And maybe we can focus on three areas only. So the new concrete class, C 100 per 115, the young modulus for the lower class concretes is now lower, and we have unified compression strengths for all classes, so 2.0 per mile and 3.55 per mile in your design. When we are comparing the design compression strength, we can see more differences here due to the additional ductility factor. So for every concrete class above C40 per 50, we have a difference, and it's up to 20, almost 24%. You can see the comparison also here, and it looks nice in the presentation, but it's not totally fair, because when we take a look at simplified compression stress block distribution, previously we have two additional factors, the effective strength and effective height factor. It's not the case anymore, so we have just 0.8 and design compression strength. So after taking this into account, we can see right now the difference is much smaller. It's still there, but it's much smaller. Next change connected with the concrete classes is the strength reduction factor in shear change. In old code, it was always connected with the concrete class, concrete strength. It's not the case anymore. You can see that it's included also in the new code in many places with different values, but in no equation there is FCK. Okay, thank you. This is all from my side. Yoni will talk a bit more about shrinkage and creep calculation according to new code.
Okay, thank you, Jan, for the presentation, and I will mostly talk about the modifications in concrete design. We start with the shrinkage and creep, and because the new Eurocode have an annex which define those models, we have implemented in the FEM-Design. And first of all, we have two methods in FEM-Design. Take the creep and shrinkage into account. We can do static analysis or quasi-static with the modification of E-modulus and shrinkage loads. So everything will be shrink and curve if you have a rebars or unsymmetrical rebars. And then we have a time-dependent analysis with the construction stages, and then you get results of all of those intermediate stages. And those new models of new Eurocode will work on both. So they are here under the properties of the walls and slabs and beams and columns, and if you click those, so it works both. And the creep model is not that different, but the shrinkage model gives bit like slower early drying with the new code, especially if you have accelerated construction schedule. This might be important for you. So it's less aggressive in the beginning with the new code, but eventually the new code will catch up. And I have the example. Here's the shrinkage model, and you can see now they follow the annex B5, which is the new code. And left side is the old code, so it will shrink faster in the beginning and curve faster in the beginning, but in the end the old code will catch up. The new code will catch up. So here's the example of TDA analysis, and it's a good demonstration how you can see how they work. Then we have some modifications in the minimum reinforcement calculations and detailing rules of elements. First of all, the Eurocode divides the minimum rebar checks in two sections. First one is for crack controls, where you have predictable crack behavior and you have predictable deformation behavior. So it's good for or important for long spans and crack sensitive structures like water retaining structures and so on. And the second part is the minimum according to detailing rules, and that is important for also for long spans, but also short spans. So if you have a like high stress part and the span length is low, so the latter part will govern that you have like a ductile behavior after the cracking. There's no sudden drop in stiffness. So that is like idea that you design rebars to ensure ductility and design rebars that it's a curvature bending moment curve is sloping upwards all the time. So we have a few new equations. I don't go too deeply into these first ones. It's just like minimum according to if you have a crack control is important because we calculate the exact cracking in FEM-Design. And we also have you can see that rules, they have been modified a bit, but there's not dramatic changes. And we also have a new simplified method if you want to simplify your life. There's Annex S, which is a totally new thing, and you can look it yourself. And here's the content of Annex X, how it simplifies those equations. But let's go to the parts which have been implemented in our software. So first of all, the old code used to have these stress checks for the elements. So it meant that if you have a lot of compression, you try to limit the compression to about the longitudinal cracking and like in certain exposure classes. Or if you want to avoid yielding of rebars, you have certain stress limits for rebars, and they were in text format, and new code will be much more user friendly, and that was one of the goals of the new code. So you can see that now they have put it in the simple table, one for the rebars and one for the concrete. So if you have to do those stress checks, now they are in one single so stable and it's easy to use. So how do you set up them in the new version of FEM-Design? First of all, here in the total concrete settings, you can set those stress checks. And the second, we have one more setting under the members, under the slabs, under the beams, under the walls, and it's here, the stress limit for the concrete. And finally, you can have them in the main report. Previously, they were in the separate table in the reporting module, but now they are part of the main report of the elements, and you can see that now they have been implemented there. Then we can talk about detailing rules of primary members. In the previous code, they were scattered all around the code. So if you want to design the beam or you want to design a column or maybe wall, there's a lot of rules. And now if you look, you have one simple checklist for slabs and one for the beams. And it is like really handy because you have single like a checklist as a designer. You just go through the points 1 to 12, and then you have detailed your beams. And there's one new thing. If you have a really high beam over like 600 millimeters, you have to add a few bars on the sides of the beam to avoid cracking. So that was not, but it's good that it's a clear list for the designer. Then the minimum rebars for the beams and slabs to avoid to prevent or to ensure the ductility of the members. Previously it was like simple formula here, like a fixed formula for slabs and beams. But now it's more complex. So the new code says that you either have to design against the cracking moment, or other option is that if the stresses are below the cracking moment, you have to leave some safety margin for the cracking moment. And what it actually means that you have to take the normal force of the section, and then you calculate the cracking moment with that normal force. And then you design your section capacity. So minimum rebars is now like a capacity against the cracking moment, which is like a more better definition of really what happens. And it means that if you have a lot of tension, you need more minimum rebars compared to the old code. And if you have a compression, you need less to guarantee ductility against the cracking moment. And how it's done in the new version of FEM-Design, if you go to the properties of the slab or properties of the beam and go to the report and go to the minimum rebar section, you can see that it's now following the rules of the new code. Instead of taking this fixed formula, we are calculating the cracking moment for the certain normal force. And of course, if you have just tension, then we design the minimums against the total tensile capacity of the concrete. Now the new thing is that we do not see square millimeters in the table. This is the state, is it cracked or bent, and there's the cracking moment, but we see the tensile capacity. So here's the requirement, and then there's the capacity. So we only see how much capacity we are getting, tensile capacity of those bars, and that is like the minimum rebars in the new code. And also for the slabs, here's the utilization graph of the slabs, and the minimum rebar checks, they are here. And it's the same. We take the normal force for the slab, and then we calculate the minimum rebars for that normal force. And then here we actually see the square millimeters, what is required to satisfy the cracking moment capacity. And a few notes, it allows to take into account the normal force and more safety if you have a lot of tensile force, and better for complex shapes because you can apply this method to any shape and biaxial cases. But of course, if you have a small bending and the main loading is tension, I will still design those minimum rebars against tensile capacity of the concrete to ensure the ductility of the section. Then we have few modifications for crack calculation. So we have an effect of stabilized cracking and also better understanding of transfer length of those between those cracks. So let's take a case. You have a foundation which have been casted like a lot before the base structure. And the new dialog in the software will ask you this: is this edge case or is this a tie case? And it can be like confusing in the beginning that what they mean by tie and edge. But let's now cast the walls to the structure. So these are cast in situ concrete. And now they are connected. And of course, when the shrinkage happen in the concrete, it will cause a lot of like tensile forces in the bottom part of the wall and compression to the foundation. So it means that if the first crack appears in the wall, the stresses cannot balance in the whole wall. So first crack will not release the stresses in the wall, and that is why it's edge case. So every time when you have something preventing the movement of shrinkage, one or two of the edges of the member in the direction of the shrinkage, then you have the edge case. So edge case is more about like the cracking due to the shrinkage with which is restrained. And then you have a tie cases, like we have a floor slab here connected between two like massive foundations. So it's only connected in the ends, and if you have a like cracking or first crack in the middle of the slab, it will release the stresses in the whole element, and then the second appears, and then the third and fourth, and suddenly there's like 30 cracks, and then the stresses are balanced. So it means that it's a fully stabilized cracking. And also if you have a like external frames or you have a floor slab over the walls, then it's also tie case. So this is a tie case, this is a tie case, and if you have a wall which is casted between existing structures, the bottom part, if it's a short wall, the bottom part will be the edge case, and the bottom part is the tie case. And the ratio limit is L divided by 2 in the Eurocode, so it depends how you want to design the cracking. Time factor, the KT, is now also not only the function of the time, but also is it like formation stage of the cracking or fully stabilized cracking. So it's no longer like a fully bound to the time. And then you have a new bonding factor here to take into account the bonding conditions of the rebars. If you want to calculate this new edge case, which was also like the water tightness requirement for certain concrete structures, now it's a part of main Eurocode, you have to apply these new principles. So R factor, which means that how much the shrinkage is restrained. So usually typical value for walls is 0.5, but you can use construction stage analysis with the TDA to calculate this one. And then you can take into account if you have wall element, that how much the element has dried before installation. So if you have wall elements like precast elements, then this is an important property. So you have either tie case or edge case, and you apply, and then you calculate cracking with this more accurate formula. And how it's implemented in the software, if you look the beam, first of all, the cracking limit state is set here, and then we have this setting of edge on tie, and then if it's a tie, edge, you have to apply R and other properties. And in the report, you can see that now it uses the new formula. Here's the utilization of the cracking. And if you go inside of the design report of this beam, and it works equally with the slabs and walls. We go here, and you can see it's a tie case, so it's not preventive in the end, only tied at the ends, and then you get your utilization for cracking. Shear design is probably those things which changes the most with the new code, so it's a more unified across all the shear design tasks. In the old code, we have this formula, and if you look the new code, it doesn't look that different. But if you actually look what's happening behind the scenes, it's previously we used experiment calibrated formula for shear design. And new the chapter is different, but also we are using critical shear criteria. And instead of comparing the shear force, we are comparing the tau, which is shear stress in plates and beams. And problems with the old code, but it was used beyond the original calibration scale. So, with the thick plates, it was too unsafe. And it doesn't take the bending into account, because bending will open the cracks in the top part of the plates or beams, and the new code will take the bending into account. And also one problem with this old code was that it was difficult to design foundations, because foundations required iteration of the perimeter, but we will go deeper to that in shear design or punching design. First of all, in the old code, we just took the shear force of the plates or beams, but the new code has more plate-specific rules, so we can average the shear, we can look the angle more. So if you look these rules, and also how you handle rebars has changed a bit, because in the old code the requirement was fully anchored rebar, and the new code we can take the effective rebar. So this is the effective rebar data model of FEM-Design. So we actually can take the anchorage into account in the shear capacity. And if you look those plate-specific rules, we have a lever arm, which is each of those finite elements will get different lever arm. And also this is the formula for shearing angle. And a totally new concept is the ACS, which is shear span. So it's a ratio between the bending moment and the shear force in the plates or beams. And that takes the bending into account. So this is actually distance to the contraflexion point of the bending moment. So bending moment 0 point, or where you have to place your shear force. So the bending moment is 0. So that's the distance to contraflexion point or shear span. Then we calculate the shear span factor, so that is new thing. And also one new thing, well, KVP takes the normal force into account, but also aggregate size, because this new critical shear criteria will take the shear with the 2 or 3 mechanism. First of all, we have a doubling action of the main rebars, then we have an action of aggregate, and then we have a compressor strut to the support. So there's like 3 mechanisms to carry the shear. And we modify this D value with these factors, which is KVP and shear span factor. So how you can do it with the FEM-Design? Let's look how it's implemented. And here we are shear designing the plates, but it's exactly same if you design. There's the cotangent. We will go deeper into that in the later sections of this presentation. But let's look the results of the shear design of this plate outside of the punching regions. So we can see VED, but we can also see tau. Tau is the shear force or shear stress of the elements. And if we go inside here, let's look what is inside of the report. So first of all, we can see we have implemented these new rules. So the shear force rules and shearing angle and normal force in that shearing angle. Then we calculate the lever arm with the new formula, which is a function of shearing angle and also Z value. Then we calculate the concrete compression capacity, the strut part of the strut analogy with the cotangent value. And when we calculate the shear capacity without the shear rebar, of course, the effectiveness factor. But here they are. So the aggregate size is taken into account with the DG, and then we have the new property, the shear or the shear span. So we can say that we are about 450 millimeters from the contraflexion point. Then we take the normal force into account with the KVP, normal force in certain direction, and then we calculate the shear capacity without the shear reinforcement in this plate. And then we get the final utilization with that data. Yeah, and it's important that you check the actual what I wanted to show, that you have to check that anchored rebar. So you have a data model of anchored rebar in the FEM-Design, and that is really handy that you get the exact right applied quantity to the shear design. So we also have one alternative formula how we can take normal force into account, and this is almost like the old code. So we have a sigma CP compression or tension of concrete. More tension you have your section, less you have a shear capacity, and that's still in the new code. But this is an alternative method of the previous method. So we calculate this sigma CP, and we still take the shear span into account. So if you want to go to this alternative design in the new FEM-Design, you go to the main settings of concrete, and it's under the main settings here. You go here, and here's the alternative method for shear design, and now it uses the new formula for how to take the normal force into account. Then we have a totally new thing. We can average the shear stresses. So typically when we have a plate, we have a huge shear force peaks in the edges of the plates and corners, whole corners, and of course close to the columns. So this is very typical. And of course, anything calculated with the shell model, which is beyond the effective depth of the slab, is totally unrealistic. So you cannot take it into account. And what is new in the new code, we have rules for this. One solution is that if you reduce the shear modulus, this is not in the code, but this is what you can do. You can reduce the shear modulus to reduce the shear stiffness, and that bit reduces those peak values compared to the linear model without any shear cracking. But downside of this method is that the deformations will increase because, of course, there's more shear deformations but the new code will give you this method that you can average the shear forces over the distance of 2D or 2D both sides of the peak value. And how you can do it in FEM-Design? Well, this is the end result when you average those shear forces. So the problem with the edges and whole corners totally go away. But how you can do it, this was the old tool we always had in FEM-Design, but the new code will give you exact values. So the 2D is the exact value how you do it. So you just draw separate peak smoothing regions. They cannot touch each other because otherwise it's considered as a one big region, and it's like two-way averaging. We just want to have one-way averaging, and then you have to set the constant shape function in the settings of software follow the recommendation of the Eurocode, that it's a constant shape along the average region. This way we can do one-way average in FEM-Design. Punching is also one of the things that changes a lot with the new code, because the new thing is that we have the critical parameter is much closer. And if you compare the formulas, they are here. Left side is the old code and the new code is on the right. So we have a bit different definition for parameter. And also old code has this problem that you have a beta factor, which will take the unevenness of the shear into account. And the new code have put that beta in one simple table. So the readability of the code has improved a lot, because there was like 5 pages of how you calculate the beta in the old code. So also in here, we are switching to critical shear criteria. And the problem with the old code was that it was unsafe for long spans when there was a lot of cracking over the punching region. It was unsafe for thick plates because it was calibrated for thin plates. And it doesn't take the bending into account, because if you have a long span, you have a lot more cracking. And it was hard to use for foundations, because it required iteration of the critical punching parameter. But that is no longer the case with the new code. That is no longer needed. And it always gives you different results for the slabs and foundations. And also you had this problem if you look this example, if you have a foundations and you have a design foundations with slabs with the old code, they were always overlapping columns. And the new code, when we are calculating the punching only at the distance 0.5 times the dV, or effective depth, we can find totally new failure modes in the foundations, because those cones are no longer overlapping in the new code. So it's more realistic, and you found those critical modes, and also you don't need that iteration, so it's easier to use. So this is the formula for old code, and you can see that the formula is exactly the same as a shear design, so it basically should give you the same results. The only difference is that the shear span, how we take the bending into account, is a bit different. So you calculate like shear span in X and Y direction, and then you average those two into one number. Kn factor is still there, how you take the compression tension into account. And what else? There's a new method to take the shear forces directly from the plate and average it, but we talk about that in the later. And then we use smeared rebars, and we have to extend beyond 2.5 times the dV plus the 20 times the diameter. But other than that, it's basically the same. But now it's a unified also with the shear design. So here is a few examples how you can use the nodal force method. So in this method, we take the nodal force of column or support directly. And in FEM-Design, it's done here. And you still have two types of punching. You have a column wall end punching, and then you have a column punching. And if you go to the settings of punching, we can set the nodal force method here. So here we take the nodal force and then use the beta factor, what we can calculate automatically, and then we can set it ourselves, just like the old code. So we take shear force, then we have a Kn factor to take the normal forces into account. So more there's the tensor, less there's capacity, and then we calculate the shear span. So we are roughly at the 800 millimeters from the moment contraflexure point. Then we have aggregate size factor, DG, and then we can calculate the exact capacity of the section with this formula. Okay, and maybe we take a more complex example how we can reduce those regions. So here are the formulas for the punching calculation of the new code, and you can see that they have been implemented in a FEM-Design. So the proximity of the holes will cut the outer perimeter, but not the inner, and then also the punching perimeter has to be stopped like half of the distance to the edge. So that is also a new thing in the new code. What happens when you have wide walls? And that's a new rule in the new Eurocode. If the distance is larger than 6 dV, and let's see what happens. Here we have an example of really wide wall in the model in here. And if we can do it as a column, but the downside is that of course it divides as it should, take the mid part away. But the downside is that we have single punching force, so it's really difficult to distinguish what is the right hand and left hand punching force. And it's better to model the actual object as a wall instead of column, because then you can separate and get separate design forces for end 1 and end 2. Then we have a concept of smeared rebar and extension of rebars, and that is more important in the new code because the cracks we calculate so closely in the column head. So there's a lot of cracking also outside of that region, so it's important to extend those rebars. And here we can see how it works in the new FEM design. So if you go to the applied reinforcement, here we can see that we have applied some additional reinforcement over the column head. And here we have extended them way beyond the recommended distance. And in this example, they are not extended to dV plus the 20 times the diameter, what is a proxy for anchoring. We check the report. If you look at the mechanical reinforcement ratio, we get 0.022, which is just the base mesh quantity. And if we go to the second column where the rebars have been extended way beyond the control parameter, we can see now we get the full capacity of the additional rebars, so the reinforcement ratio will increase. So again, the data model of anchored rebar is much more important now with the new code. Then we have an option in the new code, this was not in the old code, but new, that we actually can take the tau directly from the finite element model, and we can use linear elastic finite element model to approximate. So we don't need the beta, we can take the unevenness of the shear force directly from the finite element model. Let's see an example of this behavior. Here we have a shear force, and here we have a tau. If you want to see the megapascals, of course they are kind of same thing, and here we have a few examples. For instance, usually like the foundations are usually good candidate. We can see like the left-hand side, the punching is totally uneven, and it's really difficult to take into account with the beta factor. And here's another example of unevenness of the punching force. But bear in mind that you need really high quality finite element mesh to do it properly. So you have to make a denser mesh in close to the column head too. And you can see it like 115 on the other side and one like 47, 44 in the other side of the column. And if we now look the punching utilization, so if you have set the method to shell force method, like here, instead of nodal force method, and we take the maximum value, we can take the unevenness of the punching force directly with the finite element model, as is illustrated here. So it takes the shear force divided by dV, what is a tau, so it directly takes that value from the. And there's even option that now the new Eurocode give you this option that you can average. So if you want to get more capacity out of your column heads, there's a certain type of like shear yielding is allowed, and you can average. And also we can use same calculation, same parameter for foundations, because iteration is no longer needed for foundations like these cases. So it's much more easier to do, and probably you want to know how much it varies, and here is the end result. So the difference is not that dramatic, but because the capacity with the new code is much higher, especially with the short spans. But of course, you have a case like this other one here. The parameter is totally different in the new. And of course, the new code will give you failure modes, what the old code totally missed when you have overlapping codes in foundations. But then you can calculate it yourself. So what it means in the shear when you go into next generation of Eurocodes. First of all, you are going from calibrated formula to more complete understanding what really happens based on fracture mechanics of solids. It's a more plate specific, so it gives you more like better rules for plates, but it also gives you like specificity, so you have to follow these rules. And it gives you more unified rules between the shear and punching, because you use same formulas for both. And it gives you more realistic outcome in thick plates, short spans, and if you have a tension, you might get some bit higher capacity in the section. You get the interaction of bending, and you take also can take the aggregate size in the account in the shear. And finite element models with the rebar data models are now really important to take with the anchoring. And then a few examples how it changes when you have a shear reinforcement. And here we don't have a new method in Eurocode. We are still using the variable strut and tie method, or variable angle strut and tie. How it worked before, there is a theta angle, and you can choose it so that you can choose it cotangent theta in between 2.5 and 1 in the old code. There was no any limitations. And of course, if there's not a lot of shear force, you usually choose 2.5 to get the lowest utilization of the rebars and highest utilization of concrete. And if the shear force is really high, then you optimize the theta angle so that you don't have to increase the concrete strength or the plate thickness because of the shear. So you just, instead of that, you put more shear rebars. But the new code, there's a difference. First of all, the ductility class will be introduced in the cotangent selection of shear design or shear rebar design. So it means that you have a lot of limitations how you can choose the cotangent theta. And also the old code used simplified effectiveness of cracking factor to take the cracking of in the shear into account. Let's look the modification. Of course, also in the shear design of shear rebars, we use tau instead of V. So here are the formulas. First of all, the effectiveness factor have been modified, as you can see. The V gets more specific rules, and if you want to be really fancy, you can take the elongation or strain in your element into account with this formula. But usually you can use safe side approximations like 0.5, or if there's a lot of compression in your element, then you have to use NXG, and there's the V is 0.4. But let's talk about the cotangent. First, the previous code, it was so that you can select anything between 1 and 2.5. And the new code, it's a bit different because for ordinary members, you are limited to 2.5. But if you have a bit of compression, like Priestess members, then you can use up to 3. So you get more capacity for your shear rebar. But if you have a lot of tension, then even 2.5 is too much. So you have this limitation, and then you also have a ductility class. If it's A, the shear rebar ductility class is A, you have to reduce the allowed cotangent by 20%. And you can see it's you have to be aware of these rules, so you cannot choose the cotangent so freely as it was before. Okay, you can use like 2.5 for the ordinary members, but at least when you have a ductility class B or C. But if you have a lot of tension, then you have to be really careful. You cannot use high cotangent. Or if you have a lot of compression, especially in the middle of the beam or column, if you have a lot of compression, then you have to use NXG to design the shear. Because there's an interaction, the shear is critical in the middle of the beam, and if there's a lot of compression in that zone, then you have to use NXG. So here are the formulas. So you just selected anything between 1 and 2.5, and the new code will give you a lot more like limitations for cotangent. And the ductility class is also brought into the equation, so you have to check that one. So let's see how the cotangent is controlled in the new version of FEM-Design for the new code. So if we try to design anything with the new code, let's go to the properties of the beam, like here. And let's set the cotangent. We try to use let's use something like 2.8. And I know that there's a tension in this member. It's a part of the bracing system of the beam or the building. And then we get this warning. You can see that 2.8 is larger than allowed value for certain member. And if you go to the shear design part, where we design shear rebars of the plates or the beams, it's here. We can see that we enforce those new cotangent rules here. So everything what is written in the Eurocode is also here and controlled by the FEM-Design. So it will give you warning if you try to do something stupid. And also it checks the ductility class. So when you set the ductility class of shear rebars, you have to be careful because it's now used in the design formulas. And likewise, it's for the plates and foundations. If you have put some shear rebars, like we have here, we have a lot of shear in this part of the foundations, and then we try to design it. We can set the cotangent. So we have to set the ductility class because now it's checked by FEM-Design. Also here you have to be mindful about the angle. So if you have a lot of tension in your foundations, it's no longer allowed to use 2.5. You have to maybe reduce it. But other than that, it's same as the beam. So here is the cotangent or the compression strut check, and here is the cotangent value, and also the effectiveness factor 0.4 according to NXG. And here's the capacity. Then I want to talk about the second order effects, how they change with the new code. First of all, we have all these three methods what was in the old code. So nominal curvature, nominal stiffness, and general, they are all still in the code, but they are called a bit different. Now it's a nominal curvature. It's for local methods. Then we have a second order linear methods, which is moment magnification method. It's just a different name for nominal stiffness. And then we have the general method, and we also have a method for reduced stiffness. So it means that you put cracking factors in your model, like 0.3, 0.4, and then calculate the second order linear analysis, and then you get your second order effects. New thing is this limitation for buckling load or safety factor to buckling loads. It's exactly as the steel code had. So the safety factor for buckling has to be over 10. And if it's over 10, then you don't need to design for buckling or global second order effects. What else is new? The foundations has to be taken into account, so the soil interaction. That was also in the old code, but not in the second order part. So they have lifted in here because it's so important when you have a lot of second order effects. And the new thing is that everything what governs about the second order is moved to the Annex O. So there's hardly anything in the new code about the second order. It's tell what you should do in the Annex O. And you can see the moment magnifier method, or the nominal stiffness is still the same formula, but it's just in Annex O. Let's look first the slenderness limit. So this is the limit how you check do you need second order effects for the columns and slender walls, and it's exactly as with the old code. And if we'll now look the nominal stiffness method, you can see that this formula what gave like the cracking stiffness of individual wall or column. There's nothing in the new code, so that's why the new FEM-Design with the Generation 2 doesn't apply nominal stiffness for individual members. It's only used in the global analysis of buildings. But the basic formulas are still there. Maybe if some annex provided these, then it's allowed again. But right now there's nothing. Nominal curvature is same as before, so you can see that the formulas are exactly as they were. They are just in the Annex O. But the new thing is this thing that the design moment is more like specifically defined. This was also in the old standard. So the thing, if you have a non-sway frame or you have braced system, if you have bending moments at the end of the member, then you design your second order effects with this formula. And it's also in the new code. But this only applies to braced systems without any significant transfer load. And then you take your so first order moment is this, and the total design moment is this. Idea is simple. There's a picture in the new Eurocode. So you have a second order moment, which is distributed something like this, and then you have end moment and end moment. And total design envelope is basically this, and that's what this formula is about. It takes the envelope. There's a bit fancier method, so there's some bending moment ratio in the new code. And you have to understand, this is the important question, or important to remember. O14 is the name of the equation, how you approximate the first order moment, what can be summed up to the second order bending moment. So the software will ask you that what is O14, and here's a few examples where you can apply O14. So no here, because it's braced, so we have a lot of sway effects, and we don't need no O14. This is a soil retaining basement wall, so we say no to the O14. But here we don't have any lateral loads. We only have an eccentricity of the hollow cores, and maybe like only one side of the hollow cores have been loaded. And we might have eccentricity in the bottom, so we only have end moment case and no external loading. So we say yes to the O14. And same here, if the wind load is not very high and wall is really thick, then we do it so that we say yes to the O14. So how do you set up in your version of FEM-Design? First of all, you go here inside of the settings of the member. And we go inside here, and then it asks you, do you want to consider the bending moments when you calculate the limit slenderness? And then is the question about O14. Is it a sway system or non-sway system? And if it's a non-sway system, do you have any external loading on your element? If you don't have, then you have to select O14. And if you now look the report of the element, here is the slenderness checks according to new code, or exactly as the old code. So do you need second order effects for this element? And of course you need in this case. And then you have all the new formulas in the Annex O. And you can see we have implemented the new design formulas or design moments. So this is the approximation how you combine the first order with the second order if you have end moment case in your member. Bending moment ratio, and here are the bending moments and the second order bending. And if you have anything like a wall, same applies to here if you want to design a wall like this one. So it's exactly the same questions. Do you want to use 014 for this wall? And if you want to use it, so you have only like eccentric loading on top and bottom, no external loading, then you use 014. And if you look the report of the wall, it's pretty much, it looks now exactly as the report of the column. So it's really easy to read, and it's like column design here. So you can see that we are doing the slenderness checks. We calculate A, B, and C factors, and then we compare to the limit slenderness. And there's the new second order effects according to the Annex O. And the design moment is exactly as with the columns. So you use these fancy formulas to calculate those design moments according to Q2. So I hope that this will become like your new favorite way to check how the things have been changed. So you can calculate the same structure with G1, generation 1 of the Eurocodes and generation 2 of the Eurocodes, and then compare it yourself with the FEM-Design. I thank you. So questions we don't have. And
yeah, thank you, Joni. If you have any questions, you can always ask us down in the comments or on directly. At the end, if you are not a FEM-Design user yet, please remember you can always check our free trial on website StruSoft.com. And we thank you for today's meeting. You can contact us if you have any questions, and please follow us if you are interested in the changes in FEM-Design. We'll probably prepare more webinars and information like that in the future. Thank you.
Thank you.
Bye.